Okay, let's get started. So today we are going to talk about Shellcode. You have been using Shellcode in the homework, also computer. So today we will talk about how to design and develop those Shellcode. So here on this slide, I show a very old book, the Shellcoder's Handbook. I believe this book probably is 15 years old or something. There could be some new books. So this is a book. Basically, I learned how to do share coding, and this book talks about developing share code for different architectures from Intel to PowerPC. Okay, but the principles behind them are the same. So today we're mainly talking about the principles. So this is a shellcode you have been using for the 32-bit on the server to print flag. I think we went through this shellcode before. Basically, the shellcode does two things. First, it opens the file /flag. Then it sends that file to std out, which is a file descriptor 2. And both of them, open and send file here, we're not talking about function calls. They are system calls. That's why you can say there are two int 80 here. This is the first one. This is open. Then another int 80 here. This one is a send file. We'll have another int 80 that's a third system call, which is exit. So we do exit 0 here. So on the left-hand side, you can say this is assembly. Those are the instructions. So, but you are not directly using those so far, right? You have been directly using the bytes here. So do you wonder how do we generate those bytes from those instructions? That's what we're going to show you today. So notice that this piece of share code is, how big this is? Probably 40 bytes, something like that. Okay. In those 40 bytes, there is not a single zero, no byte there. The reason we do that is because sometimes there are some constraints. Your input cannot have a zero. For example, at a terminal, if you input using the command line argument, your input cannot have a zero. So we change this piece of share code to meet that requirement. Obviously, share code is just a piece of code. You can design it to do whatever you want to do. So here we are just sending the file. I also showed you the share code to create another shell. Also depends on your CTF challenges, or if you're a hacker, depends on what your target is. You will craft your own share code. So this is the share code for 64-bit. However, this one does have a lot of zeros that, in it. So today, one of your tasks is to remove those zeros, create a new share code, 64-bit, do the same thing, but without zeros. And you can say in 64-bit machine, we're not using int 80 anymore. There is another instruction for us called a syscall. We make 3 syscalls here, the same thing. The last one is the exit. The first one is the open, the second one is the send file. So you may wonder how far this can go, right? I mean, we can create a share code. We do not worry about those bytes. It just could be any bytes, could be readable, could be not printable, or we can create a share code without zeros. So we carefully design those instructions. For example, here you can say, the idea here is actually to move number 5 into the register EAX. But if we directly use the instruction move 5 to EAX, there will be a 0 there. So to remove that 0, instead we do an exclusive OR on EAX, making the EAX 0, then we increase it 5 times. So by doing this, we're not generating L0s. So sometimes there could be other restrictions, like your share code has to be the input, the interface will only take ASCII, not even non-zeros, ASCII. So how do you do that? How do you change your shellcode to do that? Or someone brought this really, really far. In a 2016 paper, no, 2006 paper in CCS, one of the top conferences in security. So that year I started my PhD study. So I remember this paper because I was working on system security, and I saw this English shellcode paper. This is one of the papers in the last decade that's only 2 words. The title only has 2 words. I don't want to say many papers, you know, that's few words, right, in the title. So what this paper is about is they give you a piece of shellcode like this. They automatically change your shellcode. So the output of that shellcode reads like English for humans. I'm not talking about for machines, but for humans, that reads like English. Okay, this is x86. Let's take a look. The first column is the assembly or disassembly. Second column shows the opcode of it, and the third column shows the ASCII for that. So this is a piece of shellcode. I don't know what this piece of shellcode is doing here. You can see here we do not see any int 80. So right now we're not making system call. So this is just a part of a value used for shellcode. So you can see there are some push instructions, integer multiply instructions, then another jump. So here we're doing another push, a lot of pushes, then some conditional jumps. So this is just part of shellcode. But this piece of shellcode, if you read this as English, okay, you get its ASCII. This is readable English. There is a major center of economic activity, blah blah blah. Okay, it's not perfect English, but it's readable. So imagine when you are chatting with someone using what instant messages you guys use on WhatsApp, something like that. Okay, so for example, if your WhatsApp has a vulnerability, a software vulnerability, you are chatting with someone, and someone may be sending you shellcode. You cannot even tell that's shellcode. That just looks like plain text English, but that could be shellcode exploiting your WhatsApp. That could happen, right? So this is like an example that shows how far we can bring this to. So before this paper, there were actually a lot of research, a lot of published papers on how do we separate shellcode from other traffic or some benign traffic. There could be benign data you send to me. There could be malicious data. The malicious data could be shellcode, could be exploited. How do you separate them? So when this paper came out, I remember reviewers and the community basically say the area of distinguishing shellcode, the area is there, because you cannot distinguish it. Yeah. You cannot tell shellcode apart from plain text English or other data. Okay, so today we're going to write some shellcode. So this is a very simple template. Yeah, go ahead. So basically, what was sent to the iPhone kind of like an exploit, same as what you developed so far in class. That's an exploit. That exploit may have some shellcode. Yeah. Then imagine how many interfaces iPhone has, right? There is the short message interface. There are a lot of apps. They have internet access. So as long as they take inputs and there is a bug in that software, it could be compromised. But of course, when there's different layers, the apps typically they are user-end applications. So, but you can use that as a springboard to attack the kernel's vulnerabilities. That's why, like 10 years ago, there was another popular word called drive-by download. I don't know if any of you heard that before. So drive-by download means you just visit a website, a legit website. Okay, you're not really visiting any bad websites. They are attacking you. No. Okay, just visit a legit website, but somehow that website is compromised, hosting a malicious piece of code. And that piece of code is just JavaScript. And that JavaScript will exploit the vulnerability in your browser. The JavaScript runs in your browser, right? Exploit your browser, then eventually your browser is compromised, then you maybe get another payload to exploit your OS. Then your whole OS could be compromised. So you didn't do anything wrong. You just visited the website. That's why it's called drive-by download. Okay. It was a big thing 10 years ago, but right now our browsers are much more secure now. So, so this is a template we're going to use today. Very simple, just a 3-line. Tell you the start, label start, then just the two more labels. And we're using AT&T syntax here. If you use this template, you don't have to use AT&T syntax. But anyway, you can see the examples I gave you here. This one is AT&T syntax. So this one is, I was actually using Intel syntax for this one. Anyway, so then you just put your instruction here. Then you can compile this to get shellcode. So let's say, how do we compile this to get shellcode? So let's say this file, this template will be assembly language. It's not C, so it will be .s. Then you compile use GCC. So GCC does not only compile C or C++. It is actually a compiler collection now. So it compiles, it's kind of like a driver. Okay, you give it assembly, it eventually gives this into assembler, AS. So you can use this as a driver. So we compile this as a 32-bit program, and we tell the compiler we do not need the libc library. We're not going to use it. Our code, just a several assembly. We're not making C library calls. We only make system calls. We also give a static here, then give the name of your assembly, then output this shellcode here. So what is the output here? That's an L file. Okay, that's an L file. That's a executable. So it's not really what you want. What we want is only this piece of instructions, the bytes, right? So that's why we have another tool. It's in the tool chain. The tool is called obj copy. From the name, you can say it's very similar to obj dump, right? So obj dump shows you the L files different sections. Obj copy, we can use it to copy different sections. So here we are only going to copy the section of the code. And in that code section, the only thing we have is that start function. Okay, here we have a start. Well, not necessarily a function, so it's a label. We didn't put standard library there. We didn't put anything there. That's the only thing there, right? For example, if you have a main function, the main function in C, the main function will be called by the C library function. We're not putting it there by giving no std lib, okay? Then we can dump that section, then we can get the shellcode itself, those several bytes. The 64-bit, the same thing. That's how we are going to get the bytes. So that I use our program to test if your shellcode works. So in this class today, all our shellcode will just do one job: read the file and print it out. We're not doing anything else. But your shellcode has to pass my tester. Okay. So this is the first version of the tester. I will show you several versions. This tester will execute whatever you give. This is the source code of the tester. just the main function, and we have we memory map one page here, 4 KB. So your shellcode can only be as big as 4 KB, and that page we say it's readable, it's writable, and it's executable. Then, if the page is created, what we do is we are going to read from std in. So 0 here is std in. We're reading one page from std in and put that in this address page. Then we are going to give the control to that page. Basically, if you put shellcode there, we give the control to that. So if you are not familiar with this syntax here, this is C. I can explain you a little bit what's going on here. So you can say void star. What is this? Anyone know what this is? What? What do you say? Yeah, that's right. So basically, we cast this into a function pointer. Means now we treat the page as a code, right? Then we call that function page. So basically, we give after this, we give control to that page. Okay. So that's the first version of the tester. I didn't really put this version on the server. We're not going to use this. This is a second version, which is tester long 0, which means your shellcode. Yeah. No, this is a function pointer. You see, there is parenthesis. The star is inside that parenthesis. So this makes it a function pointer. Yeah. So this is a second version, the tester long 0, no 0. So this version means your shellcode cannot have zeros. If your shellcode has 0, it will not be successful. How do we do that? Is I still read whatever you give me here. I just do a I will read whatever you gave me to a global variable. Then I will just do a string copy from that from what you gave me to that page. Then we'll execute that page. So if you have a 0, obviously the string copy will stop, right? So this is the second version. So for the 32 bits, you can say here, this one is already removed all the zeros. So this one can pass that tester no 0. But this one, the 64-bit one, cannot pass that. So your job is to change this one to make this one pass this long 0 version. Also, I have another one. This one has even stricter rules. So this one, the shellcode only can be ASCII, printable ASCII. So that's why, not really printable. As long as it's ASCII, it's okay. So here we have, as long as it's bigger than 0 or smaller than 127 is okay. So I'm only copying those ASCII copy here. Okay. So technically, this is not a printable. Printable is an even smaller set. So then let me show you how do we use this on our server. By the way, those are the apps for this week. And after this class, I'm going to turn on ASLR for this week. Next week, we're turning it off again for the format string vulnerability. Only this week, we're going to turn on ASLR. Let's try this one. Okay, so you can. So this is it's the same as other. It's the same as other challenges. This is an app. If you just run it, the app will wait for your input from std in. So if I do this, obviously it will crash the program because that's not valid instructions, right? So what you can do is you can create a temp file. Let's say let's do a touch temp. Let's just call it s.s. So that is our Shellcode source code. So this one is a 32-bit. So we are going to copy this one here. So this one should work. Should be able to pass that. So we go here. Then we I use Emacs. You can use whatever editor you want to use. So we copy it here. Oh, we also need to copy that template here. That 3 lines. Where are we? Here. Okay. So after that, let me go to temp. The reason we use temp is that's the only folder you can write. Now we can compile this using the command. Oops. So GCC 32-bit, no STD library, static. This one is S. Right? So here let's name it Shellcode. Okay. We successfully compiled this. As you can see, there is a Shellcode output. If you do a file on this, you can say this is a 32-bit. This is a 32-bit L file. You can do a what's going on? If you do a obj dump, if you do a obj dump on this one, you can say the code section is really small. So all our L file, all other L files we compiled so far, the code section is very complicated. There are many other things, right? But here, well, we can compile it to another one and say without std. Also no static. And let's compare to Shellcode 1. Okay, we'll do this. Oh yeah, there. When we do this, okay, we cannot even compile because this is not a valid program. They were looking for the main function. We don't have a main function. Okay. So you can see here, those are the instructions. Then we just do a string copy, object copy. We do an object copy. We dump it to the file called Shellcode raw. Shellcode raw. Then we get the raw file. So if we do a raw, it's not really any known file type. It's just data. Okay, it's just battery. That's because all those L file headers are stripped off here. Okay, so but this is our Shellcode. This is the pure bytes from 6A, 67 to CD80. Okay, we can verify that using XXD. You can see that's our pure bytes. And you can see some of them are readable characters, some of them are not. So this one, obviously, this one will not pass the ASCII tester. So if we just cat this one, we just cat this one to this non-zero tester, it should give us a flag. Because that is the Shellcode to get a flag. See, that's how we get the flag. Yeah. That's the file name. You can name it anything. That's the part with only the machine instructions. That's what the object copy does. The object copy copies here. We're going to dump a section. What section we're going to dump? We're going to dump the dot text section. Where do we output that? We output to Shellcode raw. Okay, the name doesn't really matter, right? Really anything. Okay. Then we just cat one here. Yeah, that's just a name. Okay. Next one shellcode is the L file set. That's where we do the GCC one. See, when we do GCC, we call it the output the shellcode. Yeah, that's another name. Yeah. Okay. So where are we? So I already put these slides on my website. So for the rest of class, you have two jobs. It's also part of your homework. So if you cannot finish here, it's part of your homework. The first one is, I think it's probably easier you work on the 64-bit first. This is a 64-bit shellcode here, not very long. You try to remove the zeros from this and let it pass the 64-bit tester no zero. Okay, after you finish that, you can try to change this piece of code and change it to ASCII. So you should pass 32-bit, the tester ASCII 32-bit. Any questions? Okay, I will walk around here to help you. So after you develop something, you can compile it and then you use the object domain, right? Then you can say the output. Then one of the bytes do not fall into the allowed range, then you think about how you change that instruction. That's basically the idea. So I already uploaded the homework 8. So basically, I'm asking to do task 6 of homework 8 first, then task 5. Also, another idea is in term challenge 3, the goal is to pass the firing / flag to the function, right? So most of you try to find the exact location of that string. Well, that works. You just need to try many times. But in our other challenges, we always have a padding, right? We always have a lock slave. So anyone here thought about how can we create something like a lock slave? Equivalent saying to the flag. So we do not have to get the exact location of that string / flag. Space will not work, but that's a good thinking. Why space will not work? Because space will be part of the firing.
right? So space, the white space on yes, snatch is quick. So at some point, you define. Well, the first time we talked about Shellcode, I told you guys we can have as many of the snatches there. We use, it's really the same thing, right? So you can put a 500 bytes of snatch in front of a flag. So when you do not need to know the exact location of the string.
Oh, just one minute. So since we are using Intel syntax, we're probably to change that line from AT&T underscore syntax to dot Intel underscore syntax. That's probably it. Well, you can also rewrite the whole thing using AT&T syntax. I'm more comfortable with that.
Oh, that's right. Yeah. Yeah. I don't think it. Next is extra long way of format string library.